Let's begin with an algorithm for finding shortest path. The kind of question we are dealing with is you are given a connected graph. So what that means is between every two vertices there is a path between every two vertices. The distance between two vertices is the length of shortest path, is the length of shortest path between them. Recall what we mean by distance. Fortunately, determining this is not very difficult. It's not as difficult as it may appear to be initially. In fact, what we'll do is we'll solve more general problem. So the situation we have is what we want to call a weighted graph. Not just connected, but a weighted graph. What is meant by that? So you're given with weight function A set of G to non-negative real numbers. That's an example. So if I have what I now do is I fix a vertex x, fix that vertex x. Get a path, given a path P, weight of P is the sum of weights of all the edges on that path. So if you take this path from x to y to z to w, so this will be 20 plus 3 plus 6, that comes to 29. I could also have gone to w using x to y to z to v and then to w. That will be 23 plus 4, 7 plus 7 equal to 34. So in this sense it's a longer path. It has a larger weight than what we found. Let's look at the path from x to v, where you can go directly from x to v. This is 100. The length of the weight of that path is 100. Instead, I can choose to go from x to y, from y to z, and then z to v, and then that's all. So 20 plus 3 equal to 23 plus 4 equal to 27. That will be weight of the path from x to y to z to v. And this is smaller than directly going from x to v. This does happen many times in practice. The way to explain this is on this road there is more traffic jam. So this is a very commonly occurring thing. The road may actually be shorter, but there is traffic jam on that road. Therefore, it is better to take longer route. Thereby, you actually save on consumption of petrol. Okay. So this is quite easy to explain. So it is better to go that way. instead of going that way. Okay? So what we are looking for is fix a vertex for every find a UV path with smallest weight. Smallest weight, smallest length, same thing. Yeah, the length here is to be interpreted as 20 plus 3 plus 4. Okay, so the length 27. Fortunately, this turns out to be not a very difficult problem. So this is the question. This is the question we have in mind. And there is an algorithm to solve this question, and that is called Dijkstra's algorithm. So that's what we'll. Okay. Being algorithm, you should sort of try to write in an algorithmic language. So let's see. Input, weighted graph and start vertex. I can sort of treat this, there is no edge from x to z. I can sort of imagine that there is a fictitious edge from x to z and give the weight infinity on that edge. If xy is not an edge. Idea behind this algorithm is quite simple. You start with that initial vertex u. There is a list that you maintain. There is a list. It's like a bag, exactly. List of those vertices from which distance. So what do we mean by distance now? Distance now has a modified idea. The distance here would mean weighted distance. Weighted distance between x to v is 20 plus 3 plus 4 equal to 27. Is that clear? And not equal to 100. Distance between x to z is 23. Distance between x to w similarly is 20 plus 3 plus 6, and that's equal to 29, etc. So you maintain a list. That are scanned. And for which the distance is found, has been determined. Stop. Okay, I didn't say it here, so I should say this here. Distance between x and y is the weight of p where P is least weight XY path. So to start with, what we do is you begin with a vertex u. This vertex is given to you. The distance of u from itself is of course equal to 0. There's nothing to check there. This is the smallest that you can get. There is no question about it. So initialization so you begin with singleton. T of u equal to 0. T for tentative. T of z is equal to weight of uz, is weight of the edge uz for all z, not in u. Yeah, I mean, let's, for the sake of doing it, let's suppose that this is u. This is the vertex u from which we have to start. What the algorithm will do to start with is, it will put u in the bag. It will then determine the tentative distances. For y, it is 20. For v, it is 100. For z, it is infinity. Is that clear? It is infinity. Just because so far you have not approached z at all. And then for w also, because u and w are not adjacent, it's also infinity. Is that clear? So that's what will happen at the initial station. T is for tentative. One is writing an algorithm. Therefore, this will keep getting revised. The tentative distance will keep getting revised because S will also get revised. S will get newer and newer elements in it. We'll keep adding newer elements to S. Iteration. Select. V naught in S. So the situation is like this. This is the S. This is such that T of V is minimum. Now what you plainly do is add that V to S. Enlarge S to add V. Enlarge it's the trouble with writing this mathematically. If one is to write a program, one would write that S is equal to S union V. Okay? So that's the S gets changed to which also you call it by S. Okay? Because you cannot every time keep having newer and newer names. That's not possible. Computer science people think of things in a different way. I mean, if there are 10,000 vertices, you cannot have the luxury of having 10,000 names. That's just not possible. You cannot have S dash and S double dash and S 100 dash, etc., etc. You just cannot do that. Okay. Then, look at all those. Now you revise. So there is a revision that has to take place. Explore all the edges of the form from V to if Vz one is such an edge. Then new T of Z, the new tentative, is equal to the minimum of old tentative. So, retain the old one and whosoever is minimum, you follow that. What does that really mean? There was a path from U to Z earlier that had that much of weight. Okay, T of Z is minimum so far. Now that you have added V to the bag, V has been added to the list. Maybe you can go through V, add that weight of that edge Vz, W, add that, and maybe what you get may be smaller. In that case, replace that path by this new path which goes through V, because you are better off. There is a different path which uses V and goes to Z. Do this for every Z. And continue. For example, if I were to apply that algorithm here, let's see what will happen. Initially, S would be U. Tentative distance of Y will be 20. Tentative distance of V would be 100. Tentative distance of Z would be infinity. Tentative distance of W would also be infinity. Then, at the next step, you see that among these tentative distances, smaller. Who is smaller among these? T of Y is smaller. Therefore, step 2. Of course, I didn't say T of U is 0, which is clear. Who are all adjacent to Y? Y has been added newly. Z is adjacent to Y. Z is adjacent to Y. Therefore, T of Z now will be the minimum between infinity and 20 plus 3, which is 23. Therefore, T of W, Y and W are not adjacent. So this will continue to be infinity. Then at the next step, Z will get added. I have not written V there. Yes, T of V. Yes, T of V still will be 100. Yes. Okay. Then, after this, the smallest weight now is that of outside S. The smallest weight is Z. Smallest distance is T of Z. So T of U is 0, T of Y is 20, T of Z is 23. Explore all the things adjacent to Z. You see that V is adjacent to Z. Therefore, T of V is minimum between 23 plus 4, 100 and 23 plus 4, out of which of course this is smaller, therefore it's 27. Okay? And the remaining things, W, yes. Now that you have added Z, W is adjacent to Z. Therefore, this should be T of is minimum between infinity and whatever. How far is 23 plus 6? Finally, U, Y, Z, V. Who is smaller among them? Yes, V is. What about T of W? Is W adjacent to V? Yes. So you just check if T of W should actually be the minimum between existing number, which is 29, and what is T of V? It's 27. So you could have followed this way, and then that way, but that does cost more. Therefore, it's better just to stick to the old thing. And then at the very last step, you also put W in the bag, and you're done. With all those distances as are determined already. Okay? At any stage here, if every vertex outside S happens to have a distance which is equal to infinity, just imagine a situation where my bag is enlarged enough, but there are all the vertices standing outside, their distance from S is infinity. What that means is, having distance infinity simply means that there is no path. There is no path from S to that side at all. That just means that your graph is disconnected. Your graph is disconnected. You could reach from S only up to these, you could reach from U only these many vertices. The remaining vertices cannot be reached from U. That is what it means. Is that clear? So they are disconnected. There is no question of talking of distance of U to that vertex because there is no path at all. The question of path with smaller weight will arise only if there is a path. If there is no path, there is no question of smaller weight. Okay. So this is the idea. All right, so okay, let me take one more example and then we'll. A, B, C, D, E. 1, 3, 4, 4, 5, 5, 2, 6. Okay, now let's see what will happen here when I apply the algorithm. S initially, so step 1, tentative of A is equal to 1, tentative of B is 3. Anything else? Because from you cannot get to those vertices at all. among these tentative distances, A has a smaller tentative distance, therefore you add A to the bag. U2. A is newly added vertex, therefore T of B will continue to be 1 because there is no edge from A to B. The edges from A are to C and D. Therefore, now these will, T of C will be 1 plus 4 equal to 5. T of D will be 1 plus 5 equal to 6. Okay? Whatever is not written here, namely, I have not written E, the tentative distance is infinity. At step number 3, what should be added? T of B should be 3, I'm sorry. Yeah. So B should be added. Revised distances, T of U is 0, T of A is 1, T of B is 3, T of C is 3 plus 5 equal to 8, but already the distance is 5. Therefore, T of C will continue to be 5 because it's smaller. It is better to go to C through A than through B. Is that clear? It is T of C is equal to 5. T of D 1 plus T of D is already determined. It's 6. The newly added vertex, it would be 3 plus 4 equal to 7. Therefore, this is better. You maintain the minimum every time. All right. What about anything else? Not yet. That's fine. Then, which one do we add after this? 1 plus 5 is 6. C. C gets added. Which way do we go to C? It is that way. So S now will consist of bigger bag U, A, B, C. T of U is 0, T of A is 1, T of B is 3, T of C is 5. There is no edge between C to D, therefore T of D will continue to be 6. Finally, but now from C you have an edge to E. Therefore, T of E, which is, you could get to C, 1 which is already 5 plus 6, which is equal to 11. Is that okay? 1 plus 4, 5, go that way. Is there any mistake? 1 plus 4 plus? Yeah. 5 plus 6. That's exactly what I've written. I'm using C. Distance to C is determined already. Okay. Then we put D in the bag. If we put D in the bag, how do we approach D? This way. Huh? Sorry? Oh yeah, there is a mistake I have made. I see that T of D is not 6 because when B got added, okay, we did, no, sorry? T of D is 6, so that's okay, T of, yeah. So all these are fine, yeah. T of, T of C is 5. T of E is 11 this way, but now I could say that it could go this way and that will become so the earlier thing that we did construct a path from U to E via C. Instead it is better to go to E via D, okay, because that is more profitable, it is shorter. And therefore that's the, so in the very last step you'll have all of these added and those will be the distances, okay. So this algorithm proceeds through modifications of this kind. And it's absolutely certain to work because at every step you keep adding one vertex. You keep adding one vertex. So finally the picture that will emerge will be like this. And you see that this is a spanning tree. It is actually a spanning tree. What one constructed here is a spanning tree. Very soon I am going to call it a rooted spanning tree. This is a rooted tree. It is rooted at that vertex U. Everything is coming out from U. Okay? So the only thing we need to prove now is the theorem that will say that Dijkstra's algorithm is correct. Dijkstra's algorithm works. So that would be the statement of the theorem. It does find the distance. By distance we mean path with least weight. Proof? The following two statements. By making induction. First statement, for all Z in S, for all the vertices that are already there in the bag, distance from U to Z, check that what we did was as soon as we put a vertex in the bag, the tentative distance remains the same. So once though I call it tentative distance, that tentative distance, once I put that vertex in the bag, that tentative distance is not going to change after that. The tentative distances change only for the vertices that are outside S, not for those that are inside S. So that is the first claim. And the second claim, for all Z not in S, T of Z is weight of a shortest U to Z path that reaches Z directly from S. Needs to understand what is meant by this. Reaching directly from S means this is your set S. Fellow's head is standing outside somewhere like this. Reaching directly means from here you start, visit some vertices in S, reach there directly. Not reaching directly means you may enter around here in S, go to some vertex. So this path will visit lots of friends in between and then will go to Z. So this is not reaching directly. Okay? Reaching directly means on that path the vertex, all the vertices except Z, they all will be in S. All the vertices, the first vertex, second vertex, third vertex, except the very last vertex which is Z itself, they are all in S. Remaining vertices are all in S. Only Z is not in. Only vertex not in S. Except Z. So what we are claiming is a kind of local minimality. It may be possible that you have a path from U to Z which doesn't go to Z directly, it uses some other things and then goes to Z, which may be shorter. But this will be taken into account subsequently in the iterative steps because these vertices will get added eventually, etc. So that is the idea. Proof. So let's prove this. What happens when K is equal to 1? This was our initialization. There is hardly anything to prove here because all it is saying is clearly of course. Yeah, I mean, what would mean to say that directly going from S to that just means that just use that edge. That is what it means. Any path. Is just the edge UZ. Therefore, this is true. This is true in case of the first step of iteration. So 1 and 2 hold. Yes, now the induction step. That is all that we need. From S, when we enlarge things, that we can go from S I want to let is minimum. Note that if there is a tie here, if there are lots of V's for which T of V has the same value, then you choose any one of them, doesn't matter. It does not matter. Then new vertex is added. To say that there is no such V amounts to saying that T of V is equal to infinity for every V outside S. And that just means that there is no path at all. There is no path from S to anything outside, which means there is no path from U to anything in V minus S. And that just means that you can only reach the vertices that are there in S. The remaining vertices cannot be approached at all. There is no way you can approach them. What do we have to prove? We have to prove those two statements. Let if Z is in S, by induction, that's exactly the point in making induction. So let Z be equal to V. So I want to say that the distance from U to V is what we'll call T of V. Let Q be a path which starts at U and ends at V, which has smallest weight. So Q is a path that begins at U, goes somewhere like that, and then ends there. This is smallest weight. Can that really happen that I actually have a path? Because what that number 2 there is saying is that when you go from S to V, directly going from S to V, what you see, T of V, is the weight of shortest path. So for anything here, there will be a vertex here on Q. We must have a vertex. W. Which is the first vertex outside S. Is it clear? I mean, Q will go inside S for quite some time, and the first time it steps outside S. Let's say it is something like this, W here. But then T of W, by definition of the way V is chosen, T of W is greater than or equal to T of V. And what that means is weight of Q cannot be any smaller than T of V. So therefore, no matter which path you choose, it's irrelevant actually. You cannot do anything better than T of V, clearly. there is a path that goes from S directly to V whose length or weight is equal to T of V. If you want to be more clever, you choose some other path, but then on that path there will be a vertex W which is outside S, the very first vertex. For any such vertex, T of W is bigger than, it is bigger than T of V by definition of V. That is the way we have chosen V. V is one for which T of V is a vertex outside S for which T of V is minimum. Therefore, okay, so that is the first thing. So we proved that the new vertex that we admitted in the bag, actually the tentative distance for it also happens to be the distance. It also happens to be the distance. Number 2, one is proved for S dash, S prime. Consider 2. Let okay, so it is like this. When you go directly from S to Z, the minimum distance is what we have called T of Z, the so far minimum distance. Okay? Then the length of shortest U to Z path reaching Z directly from is T of Z. Using 2 for S, the induction step, so the modification that we need to make is there may be paths that go from U that way getting into V and then to Z. Okay? That is the only modification. Hence, we are okay if Z is not adjacent. Then there is no question, we don't need to do anything at all. Okay? Then we don't need to do anything. We are quite all right. Difficulty will arise only when Z and V are adjacent. So let then a UZ path that reaches Z directly from S dash. This can be done in 2 ways. That's exactly what I'm saying. Either you reach directly from S or the last vertex may be V. Those are the only 2 possibilities. Either is a UZ path that reaches, yes, that is the picture, Z directly from S the last vertex, the last but one vertex on such a path is V. So, new T's head is equal to the minimum of old T's head and T of V, which now is determined to be the distance, plus weight of Vz. And this proves proving the that's it, that's the proof of correctness of Dijkstra algorithm. This is a good algorithm in the sense it's linear time. So every stage you keep adding one vertex, so it's quite a good algorithm. Moreover, what it also does for us is it finds a spanning tree for us. In case your graph is connected, it finds a spanning tree. It finds a very peculiar spanning tree. It begins with U, such a tree begins with U, and starting from U, you actually encounter all the vertices are taken into account. So let's introduce number of new terms. Definition: a rooted tree is a tree with a designated vertex called its root. I could root this tree here at this vertex, and then I can sort of redraw it. Okay? When I root it, okay, usually the rooted trees are drawn in a manner such that root is at the top and it proceeds in the way so that leaves are right at the bottom. This is sort of not a very natural thing, but that is the way it has been in vogue. I mean, the trees that we see commonly actually go up, not go down. Okay, they go up, but that is the way trees are drawn in graph theory. Okay, the root is at the top, and so it's an inverted tree. Standard parlance, it's inverted tree. The point I'm making is the same tree could have been rooted at a different vertex. That's possible. If you root the same tree at this vertex, it is the same tree, but yeah, it looks something like this. Okay. So same tree could be rooted. If you have tree on n vertices, it could be rooted in n different ways. Is that clear? There are n different ways of rooting a tree. Nothing, roughly what we are saying is, trees don't come with root. Okay, it's not part of definition of a tree. You have to define a rooted tree. Okay, and which vertex you declare as root, that's your choice. Okay, now the next thing that is rooted. Given connected graph. A tree, a spanning tree. Rooted by using Dijkstra algorithm. Yeah. The point is you really don't need Dijkstra algorithm is a high powered thing. You don't really need to use Dijkstra algorithm to find a spanning tree rooted at U. So special situation of Dijkstra algorithm is what is called breadth first search tree. BFS. What is it that we're going to do? We start with a root. So these are to be called children of that root, natural terminology. Then he has grandchildren, and then he has great-grandchildren. May have great-great-grandchildren, etc., etc. Is that clear? That is the idea of a breadth first search tree. Okay. Eventually, some of those children's children, etc., may become childless themselves, like it happened with the middle son or daughter there. Okay. But that's sort of the idea of a breadth first search tree. Okay. You can find a breadth first search tree starting using any vertex as a root, applying Dijkstra algorithm. We'll break here for a few minutes and then we'll describe the breadth first search algorithm. Okay.